It is a fact that in science, as man has progressed, we move more and more away from things that are centered upon man, as we have found for those units, with an inch and a foot and a second and all of these other things that are units really based upon the size and scope of a human and the things in their activities, to something that's more based upon things that are innate in nature, like atoms and natural links and frequencies of light and things of that nature. For one reason for this is because those are more reproducible. It's very hard to decide exactly what an inch is. What's the width of a finger? And how do we standardize that? Well, we really need it in terms of some exacting standard. Well, when we were only dealing with primitive hunters and gatherers, it wasn't that important. And if we didn't have good measurement tools, then of course we didn't have rulers and laser beams and things of that nature that could be used to do these things accurately. So in fact, we kept those old units, and different societies had all different kinds of units. For example, in Mexico for a long time the stone was the unit of weight. But now, about the time of Napoleon, when he began his vast conquest, in about the year 1800, he decided that for commerce and other reasons, he should integrate all of these countries into having standardized units. And the primary units then became a scientific international standard. The first one of those was the unit of length. And we decided on, the unit of length was decided to be the meter. Now the meter has had a long history, and originally it's now, since 1983, the distance that light travels in a vacuum in a certain fraction of a second. And therefore, if you look at this, you can say, oh, I know exactly what the speed of light is. The speed of light is this many meters in a second, and that's exactly true. So now the fastest, the most accurate way that we can actually measure a meter is to time a pulse and see how far it travels in doing that timing. But let's look at what it originally was. Originally, it was remember 10 to the minus 3 is a 1,000th, and 10 to the minus 6 is a millionth. So 10 to the minus 7th is 1/10 millionth. It was originally defined as 1/10 millionth of the distance from the equator to the North Pole. And that was done right about the time of the beginning of the metric system, about 1800, 1799. Of course, every time you wanted to measure something, and establish the meter, to take that distance and compute it would be horrendous. And so we had to reduce that to a standard. So we used that as the standard, and then we made that into 2 marks on a platinum iridium bar. And those 2 scratches on the platinum iridium bar were exactly taken as a meter. That bar was reproduced for standards in every country in the world, so that every country had their own exact standard of what the meter was, up until about 1960. So after 1960, the meter was defined in that year as this many wavelengths of krypton 86 light. And of course, we could take those wavelengths and look at interference and do that extremely accurately. Well, it was only since this 1983 that we changed that definition and were able to improve it. And so at the present time, since 1983, we use the speed of light as a standard in order to determine what the meter is. Separately, I'm going to go over the different kind of scales that we have, but I might mention that between 2 quarks, the shortest distance we could imagine, the quark to quark, in other words, within something like a proton, this is one of the smallest particles that has composition, is about a Fermi, or a femtometer, 10 to the minus 15th meters. And that's what we have when we look at a distance across a proton. It's about the shortest distance we can imagine. An atom, on the other hand, let's take a hydrogen atom. If we look at the distance from the nucleus, the proton, out to the electron, it's about a half an angstrom, and therefore this would be a whole angstrom. And this distance, called an angstrom, is 10 to the minus 10th meters. So an atom is 10 to the 5th times as large as the nuclear particle that's the proton in the center. Then, of course, we get up to the size of a human, which is about 2 meters, a little bit, of course, that's a little bit large, a little bit more than 6 feet. The Earth, the Sun, and the universe itself. One way to compute the size of the universe is to remember that the universe is about 10 to the 13.7 billion times 10 to the 10th years old. We take this and then multiply that time converted to seconds times the speed of light, and parts of the universe are expanding at the speed of light, so 13.7 billion years times the speed of light. It's how far light could have gotten since the beginning of the universe. That gives us some kind of idea. If you compute that, go back and do that as an exercise and compute that using units. And it will give you some idea of what the scale is from the smallest to the largest thing that we have in the universe. Now, for mass, the kilogram has been taken as the standard of mass, and the kilogram was originally defined as a cube of water at a particular temperature and an exact purity, that is 1/10 of a meter times 1/10 of a meter times 1/10 of a meter cubed, and therefore there are 10 times 10 times 10, 1,000 such cubes in a cubic meter. So it's 1,000th of a cubic meter of water, and that was the original definition. So water is a very good standard, and that allowed people to reproduce that standard. And that was converted to something a little bit more standard, namely a platinum iridium cylinder that was in Paris. So that cylinder that's in Paris is kept in a sealed thing, and it is the only constant that we have now that is not based upon some atomic phenomena or molecular phenomena. It is a physical mass. That will change in the near future, and there's a new standard that's going to be made using a particular type of molecule that we'll discuss later. So anyway, the kilogram is that mass, which is 1/1000th of a cubic meter of water. And we could also look, and I will show you scales later, of the mass of the electron, mass of the proton. Human, of course, we know what that is in terms of kilograms. A kilogram is about 2.2 pounds, so a 220-pound man is 100 kilograms. So a male might be 100 kilograms, and then we can make a comparison of how much mass there is in the galaxy to how much mass there is in one electron or proton. And we'll do some of those calculations later using units. Our next fundamental unit, we have here length, we have mass, and the next one is time. And the unit of time is the second. And originally, it's now taken, as this many vibrations of a cesium-133 radiation. And that's a specific number of vibrations, and therefore the second really can't be broken down into fractions of those seconds very easily, fractions of those vibrations very easily, without having something that vibrates more rapidly. Now, before 1960, it was this fraction of an average solar day, which was 60 seconds in a minute, 60 minutes an hour, 24 hours in a day. And of course, that's kind of hard to do. What is the average solar day? How do you go back and compute that? It's a lot better to be able to use a cesium radiation. And that way you can standardize it wherever you are, in outer space or in some other country. You can go back to cesium and know exactly what it is. You can find out what distance is, because you know how that light is going to travel at the same speed anywhere. And you can get pretty close on the mass of the kilogram. We have certain other units. There's the unit of electrical current that we'll talk about in a much later section. It's the ampere. It's the current flowing in two parallel infinite wires that results in a force of 2 e to the -7th newtons per meter in length. That's a force per unit length. And then the coulomb, which is the electrical charge, is defined as the flow of 1 ampere in 1 second. So if I have 1 ampere going along 1 amp, and the amount of the number of charges that pass a point in a 1 second would be exactly 1 coulomb. So the coulomb is an ampere times a second, and it's not a fundamental unit. It is the ampere that's fundamental. The next most fundamental concept is the concept of temperature. And there's a triple point of water where water, ice, and steam can exist in equilibrium. And that is at a temperature of 1/10 of a degree Celsius and a vapor pressure of 610 pascals. So if we take a container, make sure that the temperature is 1/10 of a degree Celsius, and then we take water at this water pressure, and then at that one point we will find that 273.16 kilograms, Kelvin, is defined as the temperature at which those three substances, ice, water, and steam, or water vapor, actually coexist at the same time. And that's called a triple point of water. That's when they're in equilibrium. So any one of them, like the steam is condensing into the water at the same rate as the water is evaporating into the steam, and conversely. We will do some calculations later with these various units using units.